All right, time to learn about spring force. So spring force, or the equation that is going to govern it, is also called Hooke's law. Now, you have likely played with something that is springy or stretchy or something like that, and you know that in order to stretch or compress that elastic object, you have to apply a force. We can't just think our way into stretching or compressing a spring. So we, in this version of physics, only are going to deal with objects that follow Hooke's law, which is the equation you see on your screen. There are other objects that do not follow this law, do not have a direct relationship between spring force and X. We're not going to pay attention to those right now. We start with the simplest model. So the Hooke's law equation looks like Fs equals Kx. So that Fs is the force exerted by a spring that is either stretched or compressed. And that is, of course, measured in newtons. It is a vector quantity, so it can have a direction. X is defined as the change in spring length from rest length. If you were to look at a spring, you would know that it has a length already. So we're not measuring like a final position or anything like that. We want to know a change in length. And that change in length needs to be in meters. As you read a lot of questions, you're going to see a lot of lengths in centimeters, so pay attention to that. So let's say we have a spring that has an initial length of 5 centimeters. In situation A, I stretch that spring out to 10 centimeters long, and in situation B, I compress it to 1 centimeter long. So for A, if I was to plug in a number for X to try to find the force I'd need to stretch that, or the force the spring is exerting, my X would need to be the change in length. So I go from 10 centimeters, or from 5 centimeters to 10 centimeters. So I have a change in length of 5 centimeters. But again, we got to be in meters. So I divide by 100. So my X for A would be 0.05. For B, we have a change in length of 4 centimeters, divided by 100, 0.04 meters. And then we have K, which is defined as the spring constant, which tells us how stiff the spring is in newtons per meter. Now we call it a constant, not because it is the same everywhere, but because it is constant as the spring stretches or compresses. But it is different for different springs. We all know that different springs have a different amount of stretch or compress, or different stiffness, right? If you have a clicky pen, that spring has a very small spring constant. We can easily compress it. But your garage door springs are very large spring constant. They take a lot of force to stretch or compress. So let's say we had a spring constant of 250 newtons per meter. Right? You'll notice a lot of our spring constants are in the hundreds or thousands. That's not weird. So what that means is it's going to take 250 newtons of force to stretch that specific spring by 1 meter. So that is what a newton per meter means. It's how much force we need to apply to stretch 1 meter. Now, you'll notice in your studies that the spring force equation often has a negative in it. So you'll usually see me write it as Kx. You'll sometimes see it as negative Kx or the absolute value of negative Kx. So let's talk about what that negative means and why I ignore it. Okay, so here we have a spring at an unstretched length. If I was to compress that spring and think about the force that the spring exerts on the block, that spring is going to push the block to the right. So when the spring is compressed left of the rest length, it exerts a force right. Okay? And if I was to stretch the spring to the right, that spring would be pulling on the block to the left. Okay, so when the spring is stretched right of rest length, it exerts a force left. So the spring force can push or pull, which is kind of cool. So it is this fact, or this thing, the fact that the spring force acts opposite the displacement. That's why there is a negative. Right? So the spring force is considered to be a restoring force, meaning the force acts toward the rest length to restore the spring to its original rest length. Right? Springs don't want to be stretched or compressed. Okay? So the direction of the force is opposite the direction of the stretch or compression, and that's what that negative represents. Okay? All right, so a question, right? We have a 100 Newton per meter spring, 10 centimeters long. what force will the spring exert if compressed to 4 centimeters long? So go ahead and take a minute to try to calculate that. Not too hard, right? So we should get 6 newtons. Biggest thing, of course, is remembering to convert centimeters to meters and remembering that x is not length, but change in length. Now that's the force that the spring is exerting when it is compressed to 4 centimeters. That 6 newtons is also the force needed to compress the spring to 4 centimeters. So I could kind of ask this question in 2 ways. What force do I need to apply to get it to compress there versus what force the spring is exerting to get it to compress there? Okay. If a spring is stretched past its rest length, it will exert a force. Okay. So one place where things might get kind of tricky is when we have vertically hung springs, because we start to talk about an equilibrium length versus a rest length. So let's say before a box is attached, my spring hangs vertically here. This would be called the rest length. Okay. I then attach a block and allow the block to come to a stop. This is called usually my equilibrium length. Equilibrium because that is where my net force is 0. So on the block I would have an upward spring force, right? Upward because I'm trying to restore back to that x equals 0, and a downward force of gravity. As this box travels upwards, I'm still below or down from my rest length. So my spring force is still upwards, but at this point my spring force is smaller because I'm less stretched. So what that means is if I was to try to find the acceleration of this block, a couple of things are going to happen. One, depending upon where I am, that spring force could be positive or negative, right? If my spring got squished and I was now above the rest length, both my spring force and my force of gravity are going to point down. But if I'm below that, the spring force points up. Okay? Also, this spring force is going to vary with a change in length. So at all 3 of these locations I drew, I have different x values. If I have different x values, then I have different spring force values, which means my acceleration for this system would be non-constant. Okay? So we'll talk about that when we get to simple harmonic motion, but just as a heads up. Okay? Now, there are situations where we can deal with a spring and have a constant acceleration. For instance, in a situation like this, right? If I have 2 blocks connected by a string and a force applied, okay, if I think about my 2-block system, my acceleration is dependent upon the net force and the total mass, which in this case is 2m. So since this net force is constant, right, that applied force, my acceleration for my system is constant, which means the acceleration of either of these blocks is constant. So if I was to consider block M, the only force, we're on a frictionless surface, acting on the block M system, this one, A, is the spring force. So we have a spring force equals MA, okay, so Kx equals MA. Since this acceleration is constant, the spring will remain stretched by a constant amount. Okay, so it's not like the vertical situation where we have some changing lengths. Okay. Just some things to be wary of as you are going through and solving spring force equations. Most of the time for now, we're going to be dealing with situations like this, where the spring compression or spring stretch is constant and causing some sort of acceleration that is constant, or it would just be straightforward questions like what force will the spring need to exert, things like that. Okay. All right, that is everything you need to know about spring forces.